To understand how TurbSense really works, we're going to have to look at a little bit of physics. So, nephelometric turbidity requires a light source, a beam of light, and a detector to catch the light that is refracted through 90 degrees to that detector. So we're looking at an area of turbidity within that light beam where all of the particles refract that light through 90 degrees. We collect that light, and the more turbidity there is, the more signal we get. So we end up with a situation like this. Where the detected light goes up with turbidity. And it's linear up to about 200, and then after that we linearize it with some clever software, but generally from 0 to about 200 it's a linear response. Now the way we calibrate this so that we can tell you what the turbidity is based on what we're collecting is we put in a known sample of turbidity. So for example, 20 NTU, and then we put in a 0. Now that 0 is really, really difficult to do, partly because water itself with no particulate will give you a turbidity reading of about 0.018, but partly because it changes over time. And it changes over time through noise in the electronics, through variances in the light source and in the detector, and also if there's any stray light, which is light coming from anywhere else, into that detector that we don't want. So manufacturers do one of two things. They either fix the 0 when they manufacture that sensor. Problem with that is it does drift over time. So your 0 over time will change and not be correct, particularly with regards to background light, to stray light. The other way of doing it is to ask you, the customer, to put a 0 NTU sample in the sensor. So you end up with a 20 NTU and a 0 NTU, and that's how you draw the graph. The problem with that is getting 0 NTU water is incredibly difficult. Even just opening the packet, particulate from the atmosphere will go into the water and create an interference that will contaminate that. So very, very difficult to get a 0 NTU water. So the TurbSense works in a slightly different way. It's still that the more turbidity, the more light we get, but we're taking advantage of another clever piece of physics. And that is, if I've got a fixed amount of light and I double the turbidity, I will double the amount of light at my detector. Okay, so far, that's good. What about this? What if I have a fixed amount of turbidity and I double the amount of light? I will also double the amount of light that comes to my detector. So I can increase the amount of light at my detector by either increasing the turbidity or by increasing my light output. So here I've got turbidity and detected light. What I can do is change that to be emitted light so I'm measuring now with another detector how much light I'm outputting, and that, if I double the amount of light I'm outputting, for the same turbidity I will double the amount coming at my detector. It's just physics. There's nothing clever about the TurbSense itself, it's using that physics. So I can plot detected light against emitted light. Now, if there is no turbidity at all, if I draw it on that graph, I'm drawing the axis. Because it doesn't matter how much light I put out of here, if there's no turbidity, I'm not going to make an effect. I'm not going to get any light at my detector. So no turbidity is this axis. If I put some turbidity in, I create another axis. If I put more, if I double the turbidity again, sorry, not another axis, another line on the graph, I have another line on the graph. So each of these lines on the graph represent a different turbidity. So that might be 3 NTU, that might be 6 NTU, that might be 12 NTU. You can see where I'm going, that might be 18 NTU. And that is by measuring and changing the amount of light. So the amount of turbidity here is the gradient of these lines. Does that make sense? Okay, so now I can be really clever. What I can do is I can take my detected light, divide it by my emitted light. I could have had a... So detected light over emitted light, which is the gradient of those lines. And I can plot that against turbidity, and I end up with a single line which I can calibrate. So if I put 20 NTU turbidity here, I can calibrate it. If I now halve the amount of light, that gives me 10 NTU. Physics. I've got 2 points on my graph, and I can do a regression through to 0 without ever needing to set a factory 0 and without ever needing to put a 0 sample in it. So from a single sample, utilising this clever physics, I can do my perfect calibration through 0. Now that 0 is going to be unaffected by electronic noise, and it's going to be unaffected by stray light. And it will be unaffected by stray light because if we do this quickly, this halving the light, the stray light will be the same in both cases, and it gets cancelled out. So by using this very clever thinking about physics and how it works, and by plotting emitted light against detected light, then we can use the gradient of that against turbidity to give us our calibration.